16 minutes.
After this, we can keep going to the next one.
Sounds good.
Yeah, they have a series of this. So we definitely will not finish all of it today. Okay. So they start to talk about volume rendering, which technically the term like participating media is better than volume. It has its own set of equations, which are generalization of the equations used to describe how light interacts with hard matters. So we have BRDF for hard matters, but for volume, it's a lot more complex, I assume. And they talk about, we use a so-called bottom-up approach, a practical approach. We will write code first and explain the equations later, I guess.
Not a bad way to do it.
Yep. So there will be several lessons. In this, we will study the foundation of volume rendering and remarching. Simulating the color of the sky. This can also be interesting. Well, 42 minutes, so probably can be a standalone meeting then. Our first aim in the first two chapters is just to render a volume shaped like a sphere illuminated by a single light source on a uniformly colored background. That's very disappointing. Okay, this will help us get a first intuitive understanding of what volumes are and introduce the remarching algorithm. You have a lot of constraint now. It's uniform density, and we will ignore shadow cast. And here is a pretty image that we will definitely not implement something like this for now. I guess here are some basics: internal transmittance, absorption, particle density, and the Beer's law.
Oh.
Luminance of beer.
Yeah, light is likely to be absorbed when travels through a media. participating media, and the more particles in the volume, the more opaque the volume. So from the simple observation, we have some fundamental concepts like absorption, transmission, and the relationship between how opaque a volume is and the density of particle. For now, we will consider it uniform, the density. So some light will be absorbed. And we are interested in how much light gets transmitted. We speak of this internal transmittance, which is amount of light being absorbed by the volume as it travels through. I think this is wrong. I think it's opposite, right? It's the amount of light not being absorbed.
Yeah, the next sentence confirms
Yeah.
what you're saying.
Yeah. Probably we can provide a feedback for that. Let me have a note. Yeah, I think I'm in their Discord server, so I can just tell them this, or if they are pull request or something.
So is what they're saying the opposite? Like it's the
Yeah.
internal transmittance is the amount not absorbed?
Yeah.
Higher
Yeah,
transmittance
so
equals-
0 is like everything get absorbed. 1 is like
Okay.
nothing gets absorbed.
Maybe something like attenuation there might make more
Yeah.
sense.
Beer-Lambert law. In Beer-Lambert law, the concept of density is expressed in terms of absorption coefficient and scattering coefficient, which we will introduce later. The denser the volume, the higher the absorption coefficient. It look like this. So it's exponential decay based on the distance. And I guess this is absorption coefficient.
What's EXP versus E?
It's just a same thing, I guess.
Oh, yeah.
It's just a bit redundant to write it twice, but so yeah. So the internal transmittance is exponential decay depend on the distance.
They should have shown a
Mhm.
picture of how the exponential decay works. There's a good one on Wikipedia for Beer-Lambert law. Yeah,
Yeah, I guess not everyone like can have intuition on that. So yeah, it's something like this.
I guess something to be said about the exponential decay is it moves quickly in the beginning and then has a very long tail.
Yeah,
And that's kind of the counterintuitive thing about it.
yeah. And the thing I linked, it has a picture of like of a laser going through a liquid,
oh yeah.
and you can see how it falls off really
So
quickly.
yeah, so at the start we have a very strong scattering, and then it's just lost very quickly.
It looks like this arco was linked in volumetric fog, which makes sense. Volumetric. Yeah.
Units of these coefficients is reciprocal distance or inverse length. Yeah. It helps get an intuition sense of what information these coefficients hold. You can consider the absorption coefficient as a probability or likelihood that a random event occur at any given point / distance.
So you can think of it like whenever you travel a specific distance, you lose a percent of
Yeah.
the remaining light. And,
Yeah.
and that's why the shape of the graph is exponential rather than linear or some other shape.
The coefficients are said to express a probability density.
Right, I guess it's the probability that the thing gets an individual ray of light gets scattered away or goes through unhindered.
Yeah.
But also
Yeah.
like unhindered when it travels through a certain distance, right?
Yeah.
Yeah.
Or rather, the coefficient is the probability of it being scattered through a fixed distance of 1/m or
Mhm.
1 centimeters. I guess I'm just trying to say that the probability is yeah, it's given in terms of some sort of units.
Yeah, but it's not really. You can't. It's like Jacker said. It's not linear, right?
Yeah.
So you have to choose some distance. Otherwise, the probability doesn't make sense. Because if you double the distance, it's it's whatever squared times probability that's going to get absorbed or something. I don't know.
Yeah.
Yeah, that's why it's a density. It's not not a probability itself.
Intuitively, that's just really wacky to think about, because if you take a ray of light traveling 1 meter and it has a 50% chance of being scattered, for whatever reason, it feels weird that if you double the distance it travels, I guess actually, no. You don't add the probabilities of it being scattered in the second time. You have to multiply the probability that it'd be scattered in the second one.
Not even multiply. It's like this. This is like I'm not sure I'm 100% right because I'm really rusty with probability, but I think this is like Poisson distribution. Yeah, so it's something like this exponential decay.
I guess I'm just saying that the probability of it going through 1 meter of space and then the probability of it going through another meter of space, so over 2 meters, it's not just those two probabilities added together. It's some sort of other combination
Yeah.
mode. And so it
Yeah,
doesn't
it's
give you a
an
linear range.
exponential kind of
Yeah.
thing.
But that intuitively makes sense as to why it's, an exponential decay rather than a linear relationship.
Yeah.
Excuse me.
Yeah, and the other thing is that since it's you can't, I mean, it is it's compounding, right? Like you said, like it's multiplication, but since it's like infinitely compounding, that's why where you get E from, right? Right.
Yeah.
N times 1 over n or 1 over 1 minus n to the infinity, whatever. I was trying to look that up.
And it says a probability should not exceed 1, but this number can because it's not a probability, but a probability density.
Yeah. So yeah,
Yeah, it's different. This density, like, because it has a unit, so you can perfectly exceed 1. It's just like its integral will be a density, and that cannot exceed 1. Mean free path. So inverse of the coefficient, you get a distance. This distance is called mean free path, represents the average distance at which a random event occur. Interesting.
That makes sense. I'd heard about this before, but having it be the inverse length as the unit, that makes a lot of sense.
I feel like there are some kind of math that just get glossed over, like why this is just as the average, but I guess because this is a side that they just don't bother to explain that.
So are there ray marching step sizes based on this? I wonder.
Well,
I have no
mean, in
idea.
reality, right, it has to be a photon hitting an atom, right? And those are very, very teeny. So it's kind of really glossed over. It depends on the size of the thing that you're, what you
Yeah.
mean as an event, right? If an event is running into an atom, then it's the average distance is going to be insanely small, right? And
Yeah.
so this really has no meaning, like, and
Yeah.
from a
It's
measurable thing, it's I don't know what this thing means at all, really.
Yeah, the time we spent looking at atmospheric scattering, it's really crazy just how detailed you can get when you take into account the average scattering of various atoms in the atmosphere, oxygen, nitrogen, CO2 versus smoke particles and other larger things that have a very different scattering and absorption profile. So yeah, this is very much a idealized world where there are no atoms. There's just a random chance of it not going in the straight direction.
Yeah, there are just one type of particle and it's uniformly distributed.
Yeah,
And
that
we
too.
can have this.
Yeah, so you're talking about SDF, right? So I think that step size only matters depending on how detailed your volumetric information is, right? Like
Yeah,
if you're,
this is like the precision of a numerical algorithm. It's not related to this number, I guess.
Mhm. Like, so if your data, if your volume data is very dense or like has very small, I don't know what the like cell size, then you want to take small steps in SDF, right? But if it has big cell size, you can take big steps. So it has more to do with your data than the math.
Yeah,
Will
it's
that be a
always
physical
like we
parameter?
need to have enough precision, but also not too small to have floating point error, this kind of thing.
And it also only matters if your data varies, right? Like if you just have a
Yeah.
uniform meta, you don't have to do any step sizes because you can just
Yep,
do the
yep.
analytical solution.
Yeah. Like, so I guess this chapter we will, because it's uniform, we will just go analytical. And that's why that's what this E comes from, because we can just get a solution. So we do have an exponential decay graph, but it's at here. So Beer-Lambert law returns a number in range of 0 or 1, 0 to 1. And absorbing only media is transparent, but dim image seeing through it. Yeah.
It's confusing to mention the liquid beer in the same paragraph as the Beer-Lambert law.
Yeah, because it was German scientist August Beer was the progenitor of the Beer-Lambert plus Lambert, of course. But then it talks about beer and gemstones, and it's like different beer, different beer.
Render a volume over a uniform background.
I mean, probably the best example of an absorbing only medium is a light gel, because it doesn't reflect or refract or emit.
Yeah. Yeah, this is pretty simple. Basically, just use the equation above. We analytically get a solution.
Yeah, just attenuate it by the exponent of the distance and the coefficient.
Where do they use CPapas though? I think the people want to like write this in a shader.
I mean, yeah, but it's just example
Yeah,
code.
it's the same. You can just modify this line, I guess. So up until now, we don't. We assume that our volume is black. It just darken the background. But the volume don't have to be, because they scatter lights too. Volumes can also emit light.
You're sharing your screen, by the way.
I just check whether it's our Discord. It's no, so it doesn't matter.
Okay.
I don't have secret on Discord, by the way.
Just making sure you knew.
So we basically add a volume color component. And do the
That-
interpolation. Sorry, what?
The plus there between the background color and the volume color, that would add
Here?
to the light, right? Add the both light together.
Yep.
Yeah.
This is also kind of hand wavy too.
Yeah. I mean, even it kind of says that above, and it says that the reflection is not really what's happening,
Yeah.
but let's just keep going with it for the sake
So
of.
if it was in fact emissive, right? And it was the same emissive, the same amount of, what's the word, emissivity or something? I don't know what the word. It's, the same level of emissiveness throughout the volume. Then like stuff that's coming back at you would get attenuated on the way back. So it's actually like the integral of some, function of E, so I don't know if this is right even.
This is definitely wrong.
Yeah.
This is like they use the reflection.
Yeah. But somehow it's reflecting everywhere, and everything that gets reflected makes it all the way back to you.
Also, like it's just a one number. It doesn't even follow some kind of BRDF, so it is even more like emission. But well, whatever.
If it was actually emissive, then it would just be a constant, right? It wouldn't be affected by T.
No, it would. It does matter the distance, because if you say had a volume of glowing gas, how thick the ray that goes through it is going to, how bright it is going to depend on how long it takes going through that. Because it's basically the sum of the emission over the entire distance.
I'm
I
not sure if that's
guess-
true or not, but maybe it's true.
Yeah, this is it's not like modeling reflection
Yeah.
or emission. This
It
is
is
just a
not.
very simplified view of things, and we will revisit that. This is basically saying we have two components. One is the like
Background color.
the transmissive part, and the other is the part gets scattered. And we just interpolate that.
Well, like if we're thinking about tinted glass, that kind of makes sense, right?
Thinking about what?
Like tinted glass as our like transmissive volume, then like this thing kind of makes sense.
Well, in that case, it should be like T times the background color times the tint of the volume, like the color that the volume is actually letting through. Right, if it's tinted.
I thought it's more like if the light has that color. If it is
For tinted glass, it's kind of, because it have two components like reflection and then the pass through. If you think about the glass as infinitely thin, then but then we don't have T anymore. We have something else.
But still here in this case, right, it should be like if the fog has a color, then it should be T times the color of the fog times background color.
Wait,
Because it's only letting certain frequencies through. Or something like that.
It's currently we just assume the volume is black. We just
until
darken the
now.
background. This absorption component, we don't even consider it's absorb certain color. We say it's absorbed uniformly. Only this part we consider it have color. I guess this is definitely a very simplified view, and we will revisit how to do things as we go through.
Yeah, the next snippet is multiply. Oh, no.
Rendering our first volume sphere. First check for intersection between our camera ray and the sphere. Then we can compute the distance ray travels through the sphere and apply the Beer's law. Okay, I guess that's why they use C++. Is this like a software retracer?
Yeah.
Technically, we don't need to compute the points where the re-enter and leaves the sphere to get the distance between the points. We simply need to subtract T min from T max. Yeah.
Hmm.
So after we intersect, we calculate the 2 points, we get the distance. Yeah, this is redundant. We can't just do this. And then we do our usual business as already showed above.
Yeah, if you like took the expression P2 minus P1 and subtracted the ray origin and ray direction, and factored out the ray origin and ray direction, wouldn't they cancel out? That's why it's redundant.
It's basically just this minus this.
Fun. Okay, yeah. So yeah, T0, T2, T1 minus T0 is the same. Okay, yeah. It's interesting that they include that then.
Well, as long as ray direction is normalized, right? Or a unit
Yeah.
vector.
Yeah.
Fair.
Yeah, other are just retracing stuff. And yeah, and we get this really disappointing looking sphere.
Yeah. Looks so pale and just kind of meh. MEH meh.
I definitely don't feel the mood. And we don't consider the lighting at all so far. And volumes too are illuminated by lights. And light emitted by the light source travels through the volume when its intensity gets attenuated. And it's the same Beer's law. And yeah, same Beer's law, and we get this light intensity attenuation. Something else also happens. Light emitted by a light source that is not initially travel toward eye, but also be redirected towards eye. The scattering effect, and in particular case, in scattering.
Oh, yeah.
This gets even more fun when you start incorporating phase functions.
Yeah.
Yeah. So in scatterings, the chance of light along the ray going to the camera, the chance of it being scattered towards the viewer,
Yeah.
which is going to depend on how long it takes to get to that point on the ray, because the longer it has to travel, the less likely it is to get that far, which compounds with the chance of how likely it is to be scattered towards the viewer.
For the uniform volume, yeah.
Yeah, and then it has to be attenuated by the distance it has to travel further on to get to the viewer. So yeah, distance traveled by light through the volume, and distance traveled by light through the volume again. So, bleh.
Well, and you also have to take an integral over the entire sphere, right? Because you could be getting scattering from any direction at any point, right? So it's like a double
maybe.
integral.
But I think I think maybe I don't know.
It might
maybe we
consider
can
that as a
calculate in from the
separate-
eye, so we don't need to consider any light not scattered into the eye. That way is
No,
much
I mean, I'm
simpler.
saying, so like if I pick like the point, look at this that picture, right? There's a scattering point, right? And that
Yeah.
point could be scattering from anywhere in the sphere. Any light that came to that point could have got scattered towards the eye, right?
Yeah, I know what you are talking about.
But then you
Just,
also have to say, well, that point could actually be anywhere
yeah, that point
along
can
the
be
line
anywhere.
in the volume, right? So you have to pick an integral along the path
volume,
of your
yeah.
eye path through the volume, and then multiply that times the integral of the sphere of all the light that could be coming in from every direction. So it's quite complicated.
Oh, I think it just says that in the next paragraph.
Yeah.
The multiple scattering stuff, yeah.
Well, and that doesn't actually even include multiple scattering, right?
Yeah,
I mean,
like
what I said. Yeah.
I think it does, because like if the light that is scattering into your view vision was scattered before it got there, right? That's the multiple scattering.
So for multiple scattering, are we talking about like even if like at some point it's like a light ray is scattered toward the eye, it could be like scattered back to some other direction, so we end up not seeing that photon. Is that like what multiple scattering?
So I
means?
think what it means, so like if you, there's the I ray, there's the ray that we're integrating along here between T0 and T1 for
Mhm,
scattering from the light source, right? And
mhm.
but then for every one of those rays that's going from like X0, X1 back to the light, you have to scatter along those rays as well, right? And then any point on there, you have to scatter along all those rays, right? So it's like an infinite tree of
Oh,
scattering events that could have happened before it got to
right.
the eye. Yeah.
Yeah, I
there's-
thought those are like encapsulated in the Beer's law, so that's why there's that like exponential decay.
No, I think
along
the
that
Beer's
ray?
law is just along the camera ray.
Beer's law is just absorption and outscattering.
Oh, so it doesn't apply to the light ray in some sense, or am I missing something here?
Well, I guess you would apply Beer's law to all the multiply scattered rays in theory.
Yeah, like when you're looking at that P4 point going to X4, you'd have to apply Beer's law along that path, P4 to X4, to figure out how much of the original light source made it before getting in scattered.
Yeah.
That's the attenuation through the volume.
Yeah, but for doing a approximation though, we could just do like Beer's law on the I ray, and then maybe on each of the light rays that are being scattered potentially.
Yeah.
And
So
for
is go ahead.
I was just say for multiple scattering, one way to visualize it is if you just look at that P4 to X4 array, if you imagine like halfway through that line, it bent and actually hit X0. That's multiple scattering.
Yeah. That sounds complicated.
Yeah,
We
so is
need
there-
to sorry.
So is there a way to, I mean, if someone has actually done this before, is there a way to like do path tracing kind of thing where we're just taking random paths, you know, and eventually
Yeah,
it
I feel like
converges?
that's the way to actually simulate this kind of effects if we want to do multiple scattering. Because here it seemed to be a weighted style retracing. We don't even consider integrate through the sphere. We just integrate through this camera ray, and we have a fixed like light source, which is a point.
Yeah, a very simple model would just be to ignore the multiple scatters and just figure out how much made it from P4 to X4, and then how much makes it from X4 to the eye, or from X4 to X3, and then just integrate that from all the other light rays along each step.
Yeah, still a simplified model here.
Yeah.
Well, it seems like it should be able to come up with some guy's name model of or law or whatever that tells you like if you actually integrated the whole thing, what you would get. You know,
Like
it
some
might be.
analytical multi-scattering.
yeah,
Um,
for certain shapes, you know, like a sphere or something.
yeah,
like that.
I think that's what. There's a program that I use to generate some texture, some lookup tables. MePlot, it does. I guess it's not analytical, but it computes a like a scattering, like the chance for arrays to scatter at each angle, I guess, for a different wavelength. For a perfectly spherical droplet. But I guess that's not analytical, so yeah, I don't know.
Yeah, so maybe the only method is actually Monte Carlo integration.
divide the section of camera ray into segments. Shoot the ray from the sample point toward the light source. Compute the distance and then apply the Beer's law. Yep. And estimate our integral using Riemann sum.
So it seems like this specific case that he's talking about, you could have an analytic solution because it's just an integral over E and sine or something.
It's already not analytical because when we do integral, it's like we have a arbitrary step size, so it's already numerical.
Well, I mean, I think there's an analytic solution in this specific case where you're just going from T0 to T1 and it's the distance is these lines inside this circle or sphere, or whatever.
No, you cannot do that because like this function, how do you calculate that?
Well, I mean, you can, I think
probably
you
can, but
yeah, I mean, you can calculate the distance from x0 to the edge of the sphere, and there's some, and then do Beer's law on that, right? Which is the exponent, to exponent to a cosine, and then take the integral
but
of that.
still this radiance function, like it's because see the distance here is like hard to compute shape, I guess. So this function, I just feel like calculating it analytically sounds like very hard problem. That's why they use this numerical integration rather than analytical solution. Yeah, it's a Riemann sum. So how does it translate into code? Please visit our next chapter. This is like emission level nonsense.
Oh, click the next link.
Yeah, I just feel like we already spent an hour on
Yeah.
this.
And then the next article is the same length, or if not longer.
Yeah.
Good speed run it.
Yeah. So whenever we see a reading time, we just need to multiply it by 3.
I hope you guys got all that.
Yeah.
Yeah, I feel like the reading time is definitely underestimated. Even if we don't have discussion, it's definitely take longer.
It's probably automatically calculated based on the number of words. But since
Yeah,
it's
it's automatic.
it's way harder to understand because it's technical.
Yeah.
It's more fun to talk with everyone though, because then I can ask questions and hopefully feel less stupid at the end of it.
Heck yeah.
Yeah, so I guess we will cover this next time.
Sounds good. Yeah.